Nice.
We were showing us on last week. Like this displacement restrictions. So I never had that.
I see.
Looks like got that in Brandon. So
Gotcha.
so am I.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today?
Surviving.
Surviving? It's good. Good. Surviving is better than not surviving. So just tell yourself that every day. Every day is you'll make it through to the end. Okay. All right. So today, so this is our only lecture this week. Of course, we had our midterm on Tuesday. I haven't started grading them yet, but I'm probably going to start tomorrow, and then hopefully get them back to you guys by Tuesday. Okay. At least that's my we'll see if it happens. Okay. So today we're starting something completely new. So I think the last time we met up for a lecture was last Thursday. We kind of did a little bit of a refresher on math. And so basically for the rest of the class, for the rest of the semester, we're going to be going over different algorithms for solving optimization. Okay. And so we're going to start with 1D methods this week. And we'll kind of build on it from there. Okay. Okay. And so other announcements I have to make. So homework 4 is currently in the works, and so I'm working on the solutions for homework 4 right now. I'm hoping to get that posted later tonight. I'm just kind of finishing up the last of the solutions just now. So you won't be able to do a lot of it. So I think hopefully after today you'll be able to do maybe half of it. And then for the other methods, we'll go over that next week, and maybe a little bit after, maybe a little bit of the week after, if things kind of spill over that. Okay. All right. So that's all my announcements. Are there any questions I can answer before we get started for today? Okay. All right. So let's go ahead and start the lecture today. And so again, our topic for today is called nonlinear programming. In particular, right now we're going to be going over 1D methods. So nonlinear programming is a term you'll hear a lot for the rest of the semester, because that's basically all we're going to be doing for the rest of the semester. So nonlinear programming is a very broad area of optimization. And the reason for that is because almost all modern methods kind of fall under this category, at least in some way or another. Okay? And so we're going to be going over lots of different ways to implement nonlinear programming for 1D problems, 2D problems, unconstrained, constrained problems, you know, and then within all of those things, you know, we're going to be going over lots of different methods. So it's just going to be from here on out, it's going to be algorithms on algorithm on algorithm. So you know, we got a little bit of a taste of it from the simplex algorithm from linear programming. And so, you know, that same kind of mindset, that same kind of thought process is going to be applied to it as well. Okay. But first, let's define nonlinear programming. Okay, so what defines nonlinear programming relative to the other methods? Okay. Okay. And so you know, nonlinear programming, these are optimization methods that only rely on function evaluations. Okay. I say largely because there are some accelerated methods where we use the derivatives, but you know, we're not going to go over those too much. We'll do a bit of it in multi dimensions, but you know, for the large part, we're only going over the I call them kind of the first order nonlinear methods. Okay. Okay. And so what exactly do I mean by function evaluations? That means no derivatives. And so right away, you know, we kind of set ourselves apart from the classical methods because the classical methods relied almost completely on derivatives, right? Taking first derivatives, partial derivatives, second derivatives, Hessian matrices, right? So we're not going to see any of that here. Okay, so we're just going to be doing just function evaluations. Okay. And we didn't even go a step further to say that, you know, we don't even rely on being able to manipulate any functions at all. And so we're not going to be doing any manipulation of the constraints or the objective function. Okay. And so if you think back to our previous chapter on linear programming, that's essentially what we were doing during the simplex method. So we were manipulating the constraints, we were manipulating the objective function mathematically through our pivot operations, and that's how we arrived at our ultimate solution. So we're not going to be doing any of that at all. Okay, we're basically just going to be taking our function, whatever our objective function is, and just evaluating it at certain points. Okay. Right. So what, and so, you know, this almost seems like it's more limiting than before, right? And so if we're not able to kind of work, you know, the way to kind of sum this up is say that, you know, we're not able to work mathematically with the objective function or the constraints. Okay. But this is actually really important because a lot of practical applications for optimization kind of fall in this category. And the reason for this is that, you know, the design variables, remember the design variables is ultimately what we want to, I know it's frozen, but I'm just going to talk until it gets unfrozen. the design variables are ultimately the quantities that we want to optimize. In a lot of practical applications, those design variables don't even show up in the objective function. Okay, which sounds very strange, right? And so, because everything that we've done so far, the design variables have shown up mathematically within the objective function. And so, how can we have an optimization framework, or how can we have an optimization method that does not allow, that does not allow for the design variables to even show up? Okay. All right. So let me give you an example. So this is a very common example that happens in practice. Come on, internet, you can do it. Okay. It can. Positive reinforcement. Yeah, that's awful. Well, there goes the positive reinforcement thing. All right, negative reinforcement. I have to make the internet feel bad. That's how I get the thing to catch up. Okay. So very common application for optimization in engineering practice is coupling it together with some kind of simulation technology, right? And so I think probably the most common that we see in engineering is finite elements. And so I know some of you are in my finite elements class, or maybe you've taken my finite elements class before. But the idea with finite elements is to take basically a computer CAD geometry or computer model and simulate its effects. Okay. All right, so let me kind of give you a more concrete example. So let's say that we're designing a propeller using FEA. Here is our propeller. It's gonna look like a sunflower because that's what I draw. Okay. There's a sunflower there, trust me, it'll catch up in seconds. Okay. Hmm? All right. And so when you're designing a propeller like this, in a computer, so let's say that you have a SolidWorks model for the propeller and you are going to run a simulation for it in ANSYS, right? This propeller is primarily defined by its dimensions, right? And so we have things like the diameter, okay, and we have the length of the blades, okay, and we have the width of the blades, the number of blades, right? So these essentially these are our design variables, and the performance of this propeller is going to depend on the values for what we choose for the diameter, the length of the blade, widths, so on and so forth. Okay, the angle of the blades, right? So so lots of different quantities. Okay, but this geometry, by itself is a little bit too complex for us to solve with hand calculations. So what we like to do is we like to turn this over to a computer software, maybe a finite element software like ANSYS. Okay. And then through ANSYS, we're going to be able to, run a simulation on that propeller. So let's say that we run a simulation and we get, maybe the stress distribution, maybe it looks something like this. I'm just going to fill things in. So you get the idea. So this would be like an FEA simulation result. And so throughout the design process, you may choose certain values for the diameter and all the design variables, right? And that may give you a certain kind of result. Okay. But maybe you want to optimize your design. Maybe you want to say, like, I don't want to just choose this diameter at random. I want to choose it in such a way that my design will work, energy efficiently and things like that. Okay. And so if you want to optimize your design, you have to come up with criteria at which to kind of check, how well your design is performing, right? And so in other words, we have to come up with our objective function. Okay, and so let's say the one of the objectives of this design is to minimize the deflection of the propeller blades. Okay, and so maybe when this propeller is in operation, maybe the blades are kind of deflecting by a certain amount, and you want to minimize it. So maybe this objective function might be deflection, absolute value. Okay, let me do it this way. Actually, let me do max deflection. And then depending on what you get from that, from that objective function, you would then go back to your design and then adjust the values for the diameter, the length, the width, whatever, right? And so this would kind of be your cyclical design cycle. And so you change a parameter, you do the simulation, you get the objective function, and then you adjust the values from there. And so ideally, what you would want in this situation is that you would want the optimization algorithm to handle this for you, right? That's why we're learning optimization, is to kind of automate this process. Okay. Because if you can't use an optimization algorithm for something like this, then then what are we even learning all this stuff for anyway, right? That's because that's what it's designed to do. Okay? We have one problem with this. And so if we look at our objective function here, right? The objective function that we've defined here is the maximum deflection of our propeller, right? Which makes sense. That's something that we want to minimize in our design. Okay. We have two problems with this. And so this objective function that we have right now, it doesn't contain any of the design variables, right? And so if you look at the diameter, the length, the width, the number of blades, that doesn't show up directly within the objective function. And so if we were to try to solve this method using a classical method, and we tried to take the derivative of the objective function relative to the diameter of the propeller, that would literally be impossible because the diameter does not show up mathematically in the objective function. Okay? And the reason this is the case is that our objective function, the way that we evaluate it is that we evaluate it from some other separate quantity or some other separate function. In this case, we evaluated it from a finite element simulation. And so all we get from that simulation is basically just the end result. Okay. And so even though our design variables, they're going to influence the result of the finite element simulation, we don't have that direct relationship built into our function because it's all done by the FEA. Okay. And so our objective function, it is going to change when we change things like the diameter and the length. It's just not as explicit as it was before. Okay. And so that's why we need nonlinear programming. So, basically in a situation like this, the only thing that we can do, at least from an algorithm point of view, is to evaluate our objective function. can't take derivatives, we can't, manipulate the equation algebraically, we can't, move things around, we only have, our objective function is our objective function, okay? And so what we need from here is we need an algorithm that kind of works around this framework, okay? And luckily, that's exactly what nonlinear programming does, okay? So nonlinear programming relies on just, it works by just applying the objective function itself. All right, so that's some motivation, and so when we're first the first few algorithms that we're going to go over today, it's going to kind of feel like we're trying to solve this problem with like one arm tied behind our back, because you're gonna look at some of the examples that we're doing. It's like, oh, it's very obvious what the minimum is, or oh, this would be so easy to find if we could take the derivative. But that's kind of the point, is that we're limiting ourselves. So that we can kind of, explore other methods that would work in a situation like this. Okay. All right. Any questions on any of this? Okay. So let's talk about kind of the general structure of a nonlinear programming algorithm. And so you'll see me use the acronym NLP. So NLP just stands for nonlinear programming. The nonlinear programming is long, and so I like to shorten it when I can. All right. And so, like I mentioned in the beginning of class today, there are literally hundreds and hundreds and hundreds of different NLP algorithms. Okay? In fact, if you do research in the field, that's kind of how you make a name for yourself, is you kind of develop your own method, you name it after yourself, and then you try to get everyone to try to use it. But the problem is, everyone else is also trying to do that same thing too. So it's we're gonna have a lot of methods named after just random ass people that we're gonna go over in the class. Not so much now, just because these are all kind of the foundational methods, but later on. Okay. So even though there are lots and lots of different types of algorithms, they all kind of follow the same framework, or they all kind of follow the same logic. And so before we kind of start diving into individual algorithms, let's talk about kind of what the structure is in terms of what you can expect. Okay. So all algorithms, you have to start with some kind of initial point. So you have to start somewhere, and that usually means kind of making an initial guess. Okay. And so I'll call that design point, or that initial point, x naught, vector. This is for all nonlinear programming methods, even the multidimensional ones. Okay. And this is usually found by a guess, or sometimes an informed guess. Sometimes you have some information. Okay. Step 2. And so from that initial guess, the next step is to find what's called a suitable direction. And so we have to basically, starting from the guess, we have to say, what direction should we move in, or which way should we go to try to improve our solution. Because usually from any given point, there's usually lots of different directions that we can go. Okay. And so the analogy that I want you guys to think about when we're doing this is I think I mentioned it at very early in the semester, is you can almost think of it like treasure hunting. Okay. And so let's say that you're on a sandy beach or something like that, and you're looking for some kind of buried treasure. Okay. You have to start somewhere. And then from that somewhere, you want to make sure that you're taking steps to get you closer to the treasure. Okay, so that's kind of what step 2 is. Okay. Step 3. Once we have a suitable direction that we know that if we go in that direction, it'll get us closer to the optimum or get us closer to the treasure. The next step is to actually step in that direction. Okay. And to do that, we have to find out how much we're stepping, how big of a step we're going to take. And so this is going to be to find an appropriate step length. So now that we found our suitable direction is, do we take a big step? Do we take a small step? Okay. How big of a step do we take? How do we quantify that? Okay. That's step 3. Okay. Step 4 is to, after we've taken that step, to evaluate the objective function at this new location. So after taking the step, we arrive at a new guess or a new location. And so we have to check and see, is our new point better than our previous one? Okay. Because from our initial point, I guess I kind of missed it in step 1, but in step 1, you're also going to evaluate the objective function at that point. Okay. And then now that we're at step 4, we perform a comparison, right? And so we compare our objective function at our current point, and we compare that to the previous point. Okay? Ideally, we should see an improvement, right? And so if we did our steps 2 and step 3 properly, that means we stepped in a good direction to improve our objective function. And so what we should see from step 4 is an improvement compared to our initial step. Okay. Okay. Step 5. Step 5 is a test to see if we've reached the ultimate optimum. Okay, so we're checking to see if we can stop, basically. So in other words, we're checking to see if we found the treasure. So we're kind of digging in the sand and seeing if we found it. Okay. If we didn't find it, then we just kind of repeat this process. No. Turn to step 2. And then this just kind of repeats over and over and over again until you reach kind of the ultimate optimum. Okay. Okay. I think a really good analogy for this is that kind of treasure hunting analogy, right? And so you're kind of you're kind of walking in certain directions, you're kind of digging a hole, seeing if you're getting closer, and then you keep doing that until you reach the threshold. Okay. All right, so one thing you'll notice about this is that, even though it's a fairly simple 5-step process, it doesn't really say, or doesn't really tell you how many times that we have to repeat this. Okay. And so sometimes this may have to be repeated, dozens, hundreds, or even thousands of times. Okay. And so, for that reason, for the most part, a lot of NLP algorithms are kind of designed for computers to do. Because kind of repeating these steps, even though they're relatively simple, repeating this 100 times as a human is something that's not that practical. Okay. And so what we're going to see now is that, for a lot of the algorithms that we're going to see, I'll work it through by hand just so you can kind of see the details of the algorithm. But I also have codes that are posted on Canvas that you can check for for example, and see how it's implemented. Okay. All right. Any questions on this? Okay. All right, so let's get into our first class of algorithms. So our first class of algorithms is known as elimination methods. Okay. All right, so just like the name suggests, elimination methods work on eliminating areas where the optimum is not. Okay? And so it's almost like kind of a process of elimination until we reach the optimum that we want. So as we take more and more function evaluations, we can kind of eliminate more and more of the domain until we reach the location where the optimum is. Okay. All right. So these methods are, I think they're a good place to start. It's relatively simple algorithm to understand, but it does rely on kind of one really key assumption, and that is the unimodal assumption. And so what that means is that there's only one extrema, so there's only one maximum or one minimum for the function in the entire domain. And so visually, it looks like this. And so there's only either one peak or one x. Unimodal function, maybe looks something like this. Okay. So that would be a unimodal maximum. A unimodal minimum, maybe looks something like this. Okay. Or there's just kind of one defined minimum. And kind of the general assumption is that if you continue this function, it just either continues rising on both sides, or for the left one, it continues falling on both sides. Okay. So both of these right here are unimodal. It doesn't matter if it's a max or a min, but there should at least be one, there should only be one extreme. But if a function has kind of multiple peaks, So maybe, maybe the function looks something like this, okay? Right, this would not be unimodal because we have kind of local minima and local maxima. So this is really important because with the unimodal assumption, then we know from our elimination methods that there's only one optimum, there's only one treasure, okay? And so ideally, as we take function evaluation, so let's say that we evaluate the function here, we evaluate the function here, okay? As we take kind of successive function evaluations, if our objective function is getting bigger, that means we're getting closer to the treasure, getting closer to the optimum. Okay? And so as we take successive function evaluations and as we see the objective function improve, we can then eliminate parts of the domain, right? And so let's say that, for the three x's that I drew here, we took the first evaluation there, our second evaluation was the second x, and maybe the third evaluation was the third x, okay? And so as we evaluate from 1 to 2 to 3, we see our objective function improve, right? And so once we evaluate 2, right, then we know for sure that the solution is not going to be to the left of 2, right? Or it might be to the left of 2. Let me actually draw the line here. And so as soon as we take that second evaluation and we see that it's an improvement, we know that the optimum is not going to be over here. So we can kind of eliminate that from the. And then after we take the function evaluation at 0.3, we can see that we've improved again one more time. And so if we do that, then we can eliminate everything to the left of 3 as well. Okay. Similarly, if you were to take a function evaluation, let's say we took one here. Okay. So if we took a function evaluation to the right of the peak, right, and we found that the objective function actually gets worse, it doesn't improve, that means that we've kind of searched too far. So that means everything to the right of 4, we can kind of eliminate. And so eventually through our methods here, through the through the elimination, oh wow, froze at an interesting time. We'll start to kind of narrow down on where the optimum is. Okay. And so for this case, we know exactly what the underlying function looks like because I drew it. But remember, for most times, you don't know where it is. So you're only just kind of taking singular darts. You're just trying to see where they land. Okay. And then based on the values of those evaluations, we can then kind of narrow down our search radius to find the where the object is. Okay. Okay. And this only works when we have a unimodal function. Because if we had multiple modes and the function kind of oscillates in value, then we can't do these elimination methods. Okay. Any questions on this? Okay. And so let's start with kind of the very, the most basic, elimination method, which is called unrestricted search. So an unrestricted search, we're basically going to do the exact algorithm that I just described, except we're not going to be restricted at all. So we're gonna search basically the entire domain. Okay, so let me write down the algorithm. Okay. And so this is going to be quite familiar to you, or at least this format. Because remember, an algorithm is different than like a formula. An algorithm is a set of kind of logical steps that you apply. And so each new algorithm that we learn is going to be kind of presented in this way as kind of a step-by-step process. Okay, so step one. So step one is to start with the initial guess. And we're only looking at 1D functions for now. So I'm gonna call that initial guess point x naught. Okay. We're going to evaluate our objective function here. So let's say we're going to take f of x naught. Okay. Okay, so we have our initial guess and we have our initial function evaluation. Okay. All right. And so the good news is that in 1D, finding a direction is not that difficult. You either go left or you go right. Okay. And so let's say that let's assume that we know our step size. And so assuming a step size S, okay. So step size is something that will be given to you most of the time, but you can change it. You can change the step size as you go along, okay? And we'll talk about that in a second. Okay. And so using the step size, let's compute a new point. Okay? And so I'll call this x1. And so x1 is going to be x0, which was our initial point. Okay. And then our new point is either going to be plus or minus s. Okay. Okay. And so the next step is we need to determine whether we should go left or right. Okay. And so we're going to compute our objective function at both the plus and the minus s. Okay. And so we're going to compute f of x0 plus s and f x0 minus s. Okay. And so what you should find is that, if our function is unimodal, then one of these is going to give a better value of the objective function than the others. Okay. And so we're going to save that direction. And so we're going to remember that, let's say that, we get a more optimal objective function when we move to the right. And so we're going to say, we're going to move to the right, from now. Okay, and then effectively what we're gonna do is we're gonna eliminate everything that's to the left. Okay? So that's step two. Step two is to find our direction. So now that we know the direction, the next steps is just to kind of keep taking steps in that direction. Okay, so step three is to take another step. In the direction found from two. And then depending on if we see an improvement, then we may choose to keep doing steps. Okay. And so we have two possibilities here. Okay? And so the first possibility is that if we see improvement in the objective function, if the objective function improves, then what we're going to do is we're going to continue taking steps in that direction. I.e., we're going to just keep repeating step three. And so we're going to take a step, evaluate our objective function. If it improves, we take another step, evaluate our objective function. If it improves, we keep doing this. Okay. All right, the other possibility is that our objective function does not improve. It either stays the same or it gets worse. Okay. And so if the objective function does not improve, that means we've basically found the optimum, right? And so we've either passed that peak, or we're at the peak and we just kind of missed it. Okay. And so from here, there's a few things you can do depending on how precise you want to be. Okay. And so if you kind of reach a situation where your objective function doesn't improve, that means your peak technically may be in between the last two steps that you took. Okay. And so if you want, you can continue to refine your steps until you reach the peak with the desired accuracy. But usually, for most cases, once you kind of reach that point, then you just terminate the algorithm right there. And so when we terminate the algorithm, we basically just take the last point before this current step. So the last time that the objective function improved, we take that as the optimal point. Right, and so that's the basics of the elimination method. Okay. There's one more small wrinkle that we can make with regards to the step size, but I think I'll wait till after the next example to discuss that. All right, any questions on this? Okay, all right, so let's do an example. So we've been talking a lot about kind of just concepts and general stuff today. Let's make sure we do an example before we go home for the week. Okay, so let's find the minimum of the following function. F of x, 2x times x minus 1.5. Okay. So let's use unrestricted search. Okay. And so if we're going to use unrestricted search, we need two things. And so we need our starting guess, our initial guess. So let's say our starting guess x naught will be 0.0. Okay. And let's start with a step size of 0.05. We may adjust the step size later, and we'll kind of talk about kind of reasons why you would want to do this. And so now from here we can just initiate our unrestricted search algorithm. Okay. So let's start with step one. Okay. Step one is evaluate. Well, we've already been given our initial guess, and so we don't have to guess for that. And so now we just have to evaluate our objective function at that initial guess. Okay. And so let's go ahead and evaluate this. So our initial guess is x naught is equal to 0. Okay. So let's plug 0.0 into the objective function. So we have 0.0 times 0.0 plus 1.5. And so of course this is equal to 0. Okay. So that's kind of where we're starting from. So we're starting from an initial point of 0. And then we're seeing if it's seeing if we're going to improve on this objective function. Okay. And keep in mind that we're finding the minimum. And so an improvement of the objective function would be a location where the objective function gets smaller. Okay. Okay. Step two. Step two, let's find our suitable direction. And so our suitable direction here will be, well, we're gonna have two test cases, so we'll call it x plus. So x plus will be 0 plus our step size, so 0 plus 0.05. Then x minus will be 0 minus 0. Okay, so let's go ahead and test those quantities. So this is positive 0.05, negative 0.05. Okay. And so we'll call the plus direction, we'll call that f plus. Okay. So f plus of 0.05 is going to be equal to, we plug it in, we get minus 0.0725. Okay. We have f minus of 0.05. I don't have in my notes, and so I'm going to, it kind of tells you which direction we're going to go, but let's calculate it just in case. Okay. The minus 0.05 multiplied by minus 0.05 minus 1.5. minus 5 by minus 0.05. 5. Okay. And so this gives us a positive 0.077. And so from this, you can see which direction is suitable to go. Because the only direction that leads us to an improvement of the objective function is the positive direction. Okay. And since we're assuming that our function is unimodal, and so there's only one peak, or in this case, it's going to be one minimum. That means if we keep going in that direction, then we're going to hit the minimum eventually. Okay. So then we have step 3. So step 3 is to keep taking steps in that direction. So keep taking steps to the right. All right. And so our next candidate for X is going to be our previous candidate, which was 0.05. And if we take another step, we're just going to add another 0.05 to it. Okay. So 0.05 plus 0.05 is 0.1. Okay. And so if we evaluate the function at 0.01 or at 0.1, 0.1, 0.1 plus 1.5. This gives us an improved value of 0.1 minus 0.1. And so you can see from this here that this is an improvement. Right, because minus 0.14 is less than minus 0.0725. Okay. So let's keep taking steps. Okay. And so since we're going to keep taking steps in the positive direction, remember what we're doing kind of in the meantime is we're eliminating everything that's to the left of where we are. Okay. So all design points less than x is equal to 0.1 are now eliminated because we know for sure that everything to the left of that is going to have less or a less optimal objective function. Okay. Okay, so let's take another step. Okay, and so if we take another step, we're just going to add 0.05 to it. And so let's take our previous guess, which is 0.1. Let's add 0.05 to it. Okay. So that's going to give us 0.15. Okay. And so if we evaluate this at 0.15, which I don't have as either, so let me go ahead and do that real quick. Okay. So this gives us about minus 0.2025. Okay. So you can see here we've again seen an improvement, right? Because minus 0.2025 is less than minus 0.14, and so we can go ahead and keep going. Okay. And so, I'm gonna kind of slow down a little bit because you can see how this kind of gets a little bit repetitive, right? And so you kind of you take a step, you evaluate, you see if it's better or not. It's not, then you keep, or if it is better, you keep going, okay? And so you do that again and again and again and again, okay? And so let's take a moment here to kind of pause, and kind of make a comment about the step size, okay? And so up until now, we've basically assumed that our step size has been fixed, right? And so we haven't made any adjustments to the step size. Right, so every time we take a step, it's only in the amount of 0.05. Okay. But that's not a limitation. We can actually change the step size as we go through the algorithm. Okay. And in fact, a lot of times you may want to change the step size. Okay. And so there's there are kind of two situations on which you may want to change the step size. Okay. And so the first one, the one that we're seeing now, is that if we're basically seeing that progress is a little bit too slow, right? So we're getting closer and closer to the optimum, but our steps are so small that we have to kind of we have to evaluate the function many times. Okay. But in theory, you can do unrestricted search, and you can do like a very small step size. You can have it be like 0.000000000001, right? And so eventually, right? And so if as long as you keep taking steps and you're still seeing improvement, eventually you'll reach the optimum. It just may take you, several billion steps to do that, right? So maybe that's not optimal. Maybe you don't want to burn out the computer like that. Okay. And so in a situation like this, you may want to increase the step size to accelerate your search. All right, so that's the downsides if your step size is too small. Okay? If your step size is too small, it just takes a long time. On the other hand, you can also have a step size that's too large. And so if a step size is too large, you'll be able to take steps very rapidly. But what can happen is that you can kind of miss the peak, or you can miss the optimum. Okay. So there's kind of a balance, and you know, because every problem is different, every objective function is different. You know, it's hard for me to tell. It's hard for me to kind of give you kind of general rules. But you know, I can at least give you kind of the patterns that you can at least see. Okay. And so of course the right step size is the perfect step size, so the one that gets you to the optimum in one step. But a lot of times you don't know what that is beforehand. And so kind of a good thing to do is maybe try out a few different step sizes and see how that affects your results. Okay. Okay. All right. Any questions on this so far? Okay. And so with that in mind, let's go ahead and continue this example. And you know, what we're seeing from this example right now is that, you know, we're getting closer, we're getting warmer to the optimum, but it's taking us kind of a little bit too much time to get there. So let's increase our step size to kind of accelerate our search. It also increase the internet speed to accelerate this this issue. It's going on strike. It's ahead of me. That's for sure. Come on. There you go. Good internet. Good job. Okay, so I'm going to present the rest of the data from this example just in a table. Okay. Okay, so I'm going to say let's make a column for xi. So xi will be kind of the current location. S will be the step size. And then f of xi will be the function evaluation at that location. Okay. So I'm actually going to start from the initial point. Okay. And so the initial point we started with 0.0. Our initial step size was 0.05, and when we computed that, we got a function evaluation of 0.0. Okay. All right. And so after that, we found that the direction that we needed to step was to the right. Okay. And so we take one step to the right with a step size of 0.05. We end up at the location 0.05. Okay. For that first step, let's keep the step size the same. Okay. And so when we evaluate the objective function at 0.05, we end up with minus 0.0725. Okay. Which of course is an improvement, and so we're going to keep going. And so our next location is going to be 0.01. Okay. And so if we evaluate the objective function here, we get minus 0.14. Okay. And so at this point, we're starting to get impatient. And so let's go ahead and accelerate our search here. And so at this step right here, I'm going to increase the step size. Okay. I'm going to increase the step size to 0.1. So that means our next location is going to be 0.1 plus 0.1, which is 0.2. Okay. And so if we evaluate the objective function at x is equal to 0.2, then we get minus 0.26. And of course, that's an improvement as well. So let's accelerate again. Okay. Because we're starting to get impatient. This is starting to become tiresome. And so with the step size of 0.2 and our previous location at 0.2, we do 0.2 plus 0.2. That gives us 0.4. Okay. The objective function here is minus 0.56. which is still an improvement, and so we still have a ways to go. So let's increase our step size again. So we increase our step size to 0.4. That means our next location is going to be 0.4 plus 0.4, which is 0.8. Okay. And so if we evaluate it there, then we get an objective function value of 0.16. Okay. Okay. And so at this point, we can see here that in between these two steps right here, the objective function got worse. So that means our optimum value technically is going to be in between 0.4 and 0.8. Okay? Because we've already eliminated everything to the left of 0.4. And now that we've evaluated at 0.8, we can eliminate everything to the right of 0.8. Okay. All that, I know it's frozen, but all that's basically saying is that, we can eliminate everything to the left of 0.4, everything to the right of 0.8. Okay. And so technically our optimum is somewhere in between there. So it should be somewhere between 0.4 and 0.8, which technically is kind of a large range. But for now, I think we're content here. Okay. And so once you kind of reach this point where you can stop, then you can kind of terminate the algorithm. Okay. And so from here, we basically take the best location. And so the best location here is x is equal to 0.4. And so we take that as our optimum. So we say x optimum, in this case, 0.4. Right. Any questions on this example here? Okay. All right, so we have about 3.5 minutes left, and so I did want to show you the MATLAB code for this. Okay. And so if you go to our course website, 4, 3, okay. I'll go ahead and post this in the week, because I don't think we did it, or I don't think I posted it for the week here. But you should see a MATLAB code there for unrestricted search. Okay. So this code right here is basically the implementation of the previous example we did in code. Okay. Okay. And so you can see here that it does everything that we did by hand except in code, right? And so we have our initial point, and I wish I could draw on this. Okay. Maybe I'll do a PDF version for next time. But if you look at kind of the first two lines right there, I tried that earlier. It didn't show up. Oh, on the Zoom thing, yeah, that's actually good. This thing. Oh, anyway, I'll figure it out for next. But just because we're almost out of time, I want to make sure that And so you can see from the first couple lines right there, we have our initial point x naught. We have f naught, which is the initial objective function, and we have our initial step size of 0.05. Okay. Okay, and so the next thing that we do there, you can see from my comment, is that we're going to determine if we need a step to the left or to the right. And so we're going to see if we get an improvement, either plus or minus. Okay. And so, if we, and so what I did was I evaluated the objective function at one step to the left and one step to the right. And then depending on that result, then that gives us our step direction. Okay. Right, and so from here, and so in this code here, I actually don't change the step size, and so I basically just use that while loop to continue stepping until we reach a point where we don't improve it. Okay. Right, and then once that's done, then it'll print kind of the optimal value, and then that is that. Okay. All right, any questions on this code here, or anything that we've discussed today? Okay, all right, so that code is available for you on Canvas, and so I'll post it in the week 8 week. Okay, and so when we come back next week, we're going to move on to our next set of methods, which is called interpolation methods. Okay, it might take us the whole week to do interpolation methods because they're a bit more complex, but they are more flexible than this. Okay. All right, so thank you guys for coming today. Hope you guys enjoy the rest of your day. Hope you guys enjoy your weekend, and I will see you guys next week.
So just over there. At 0.4.
Yes. Mhm.
I calculated it in those.
Yeah, I think I tried to skip the line.
When I took the derivative, I got 0.75.
Hmm.
So it's
Might have-
like.
Might have skipped a line because I was kind of, this was kind of offset here. And I was kind of, okay, I know, okay, I did skip a line. So yeah, so actually this thing kept going until 1 piece. I got these two columns mixed up. Because I had the conflict step, that one, and then the xi is the second column. I swapped them because I thought it'd be kind of easier. I end up getting
Okay.
yeah, so you're right. So the f of 0.8 is actually minus 0.6.
Yeah.
And then the f 1.6 is the 0.16 that I had. Yeah. That's why I skipped a one because I think okay. Mhm.
You can help me real quick.
Sure.
So I tried to do the thing you told me to do on Tuesday, but it wasn't actually working. So actually, I don't know why I didn't do it with you. The contact. So if I make the target just the edge.
Yeah. Yeah. So so when you have to define the contact and the target here, it actually matters which one is which. Because ultimately, what you're doing is you're mating these two things. But the way that it's kind of implemented in ANSYS is that it expects the target to be the bigger searches. And so if you right click on this here, and you click on split contact and target, then it's what you click on that. And so because the contact here is an edge is always going to be smaller than a face. So the face should always be the target, and the contact should be.
So the contact was the bridge and the target was the side of the.
Exactly. Yeah.
It worked.
Yeah.
I deleted it when it didn't work.
Oh. Yeah, there's a quick one because I know people make that mistake all the time. Yeah.